Okay, we are in section 2.3, differentiation formulas. This is typically the easiest of all of the lessons of the derivatives, and this is usually the one that most people are looking forward to. If you've had any inclination as to what we're heading to, this is going to make taking derivatives quite a lot easier than what we've been doing, and a lot shorter, that's for sure. So let's go ahead and we're going to take a look at a few of these things right here. We want to find the derivative of a constant. So the idea is pretty simple. This right here represents the function. That's basically your f of x. So if f of x, or y equals 10, that's just a horizontal line. Maybe right there, we'll call that y equals 10. Well, keeping in mind that the derivative is really just the slope, what's the slope of y equals 10? Well, it's a horizontal line, so the slope is 0. In the next one, the derivative of -2. Once again, that's like y equals -2, so maybe that's like right here. Once again, that is a horizontal line, and the slope of a horizontal line is 0. The next one, the derivative of 1. Once again, a horizontal line. I think you get the idea. The slope is 0. So what we can say is that the derivative of any constant, c, is 0. That's it. The derivative of any constant is 0, and because a constant literally as a function is a horizontal line. So the derivative of a constant is 0. Now we're actually going to go ahead and prove that real quick. We're going to actually use our limit proof just to show that it still works. So if we were to take the limit as h approaches 0 of, well, the function itself is c. So if I was to plug x plus h in, there's nothing to plug it into. So it's still just c. So f of x plus h is still just c because there's no x's to plug anything into. Minus the function itself, which is c over h. Always simplify your limits before you evaluate them. Well, c minus c is 0. Again, simplify your limits before you evaluate them. 0 divided by h is 0, and the limit of a constant is the constant, so this is 0. That is f prime of c. So the derivative of any constant is 0. Pretty straightforward, pretty easy. Hopefully that's a concept that makes sense. Again, remember, you're just thinking of derivative in terms of slope. It's horizontal line. Pretty easy to see that the derivatives will be 0. All right, so now let's look at some different functions, some of which we should probably already know, but if we don't, let's figure them out. So we want to take the derivative of x. Remember, this is like y equals x. You should probably have a pretty good idea that if I'm talking about y equals x, you should already know what the slope of this is. But we can kind of sketch it just to make sure. Y equals x looks like that. And the slope of that particular line, y equals x, is 1. All right, well, let's show the actual algebraic proof. So let's take the limit as h approaches 0 of, now in this case, I do have an x value here to plug something into, so I'm going to plug in x plus h minus f of x, which is x over h. And then this is pretty easy to simplify. Again, simplify before evaluating. So on top, I've got an x minus x, which leaves an h over h. And you might look at that and say, well, if I plug in 0, I get 0 over 0. Yes, but we haven't simplified it yet. So really what we're taking the limit is, the limit as x approaches 0, h divided by h is 1. So the limit of 1 is 1. That's f prime of x. Specifically when our function is y equals x. The derivative is 1. All right, and as seen with some of the past problems, some of the stuff that we did in a prior lesson, we've already done the derivative of x squared. We did that the long way, and we ended up getting 2x. So if I was to tell you that the derivative of x to the fourth is 4x cubed, you might already have figured this out, but if you haven't figured out the pattern, if I was to tell you that the derivative of x to the 10th is 10, x to the 9th, maybe then you can see what's happening here. Literally, all we have to do is we have to bring the exponent out to the front and then reduce the exponent by 1. So if I wanted to put this into some general term, the derivative of x to the n power, where n is just a number, is bring the n to the front and then reduce the n by 1. This is what is called the power rule for taking derivatives, and it makes taking derivatives so much easier. Hopefully you can see that you would probably not want to do x plus h to the fourth power if we were dealing with this one. While that wouldn't necessarily be awful, imagine doing x plus h to the 10th power with that one, expanding all that out, trying to simplify everything, divide everything by h, and then eventually simplifying everything down to 10x to the 9th. Yes, it does simplify nicely, but it would be a pain. So this is what somebody a long time ago started to discover. Oh, there's patterns here. This is what's happening. So this is what's happening with the derivatives. Believe it or not, they probably did do all this stuff the long way a long time ago until they figured out the patterns. All right, so let's practice a few of these. Other than the fact that they've used some different letters here, nothing really changes. Now, what is very important here is notation. When we calculate the derivative, for the first one, I know the derivative is going to be 5x to the fourth using our power rule, but we can't just write 5x to the fourth. We must write a notation which says, oh, f prime of x, because that's what I'm evaluating, is 5x to the fourth power. Again, bring the exponent out to the front and reduce it by 1. Now this works as long as your variable is the base and you have some kind of a numerical exponent. So the rest of these should be pretty easy. F prime of x is going to be 98x to the 97th power. Okay. F prime of t down here, same exact idea, just because the variable changes doesn't matter. 7t to the 6th. Now you do have to be a little bit more careful on the next couple. So in the case of f of t equaling 1 over t cubed, right now this is not a constant, this is not a variable base raised to a power, but we can make it that way because we can bring that t cubed up to the top and rewrite that as t to the negative third power. Now it is a variable base with a constant exponent. Just because it's negative doesn't matter. So the only thing you have to be careful of here is make sure when you take the derivative, you actually subtract 1 from the exponent. So you still bring the exponent to the front, and now we'll subtract 1 from the exponent. So negative 3 minus 1 is negative 4. So that's your derivative. And then, of course, you could rewrite that as negative 3 divided by t to the fourth if you had to rewrite it without any kind of negative exponents. But either way, both of these things are the same. So this one's still fine, that one's still fine, either way. Okay, likewise, in the upper right-hand corner here, the f of x equals, in this case, the square root of x cubed. We need to make that a just an exponent term. So we're going to have it as x. And if you remember, it's the power divided by the root for the exponent. So it's x to the 3/2. Now we can take the derivative. So we're going to get f prime of x, bring the 3/2 out to the front, and then reduce the power by 1. So 3/2 minus 1 is 1/2. And there's your derivative. Okay, same exact thing, except the next one's got an r in it. F prime of r is going to be 3/5 r to the 3/5 minus 1. So you have to be able to add and subtract 1 to fractions here pretty easily, but 3/5 minus 1 is going to be negative 2/5. It's the same thing as saying 3/5 minus 5/5. so negative 2/5. Okay, and again, you could rewrite that without the negative exponent by putting the r in the denominator. Not going to worry about that. Okay, f prime of m. Bring the negative 4/9 out to the front. Reducing 4/9 by 1. So 4/9 minus 9/9, because that's 1 in terms of ninths, is going to be negative 13/9 as my exponent. And then the last one, just because I wanted to make a really big number, f prime of x is 1000x to the 999. And that's it. That's the power rule in general. Now we're going to start throwing some extra stuff in there, but that's what you're doing. Okay, hopefully nothing too confusing there. Okay, so now we have this thing which is called the constant multiple rule. It's not really anything that you have to like memorize by definition. You just kind of need to know how to use it. The constant multiple rule says if c is a constant and f is a differentiable function, meaning that the derivative exists, we can actually take the derivative and it exists, then the derivative of some constant times f of x is the same thing as the constant being pulled to the front and then taking the derivative of f of x. So very much like limits, it just says that I can pull a constant out to the front, take the derivative, and then multiply the constant back in if I so want to. You're going to find that we probably won't do that a lot, but that is one of the rules. So let's actually prove it. Otherwise, I'm just telling you something and you're like, well, you told us that. But okay, well, here's how it works. So g prime of x is going to equal the limit as h approaches 0 of f of x plus h, so that's c f of x plus h, minus f of x, which is cf of x, because that's the function, over h. Okay? Now that we're dealing with a limit, on the numerator, I can actually factor the c out. So I get c times f of x plus h minus f of x all over h. But remember that c is a constant, and now that we're dealing with limits, we know that we can pull a c out to the front of a limit. So that's the same thing as c times the limit as h approaches 0 of f of x plus h minus f of x over h. But if you're really paying attention, this piece right here, well, that limit is literally the definition of the derivative of f. So that whole thing in red is really just f prime of x. So what this ultimately gives us is c f prime of x. So it literally just says that I can take the derivative of the function and multiply the c in later. That's it. So you can pull a constant out to the front if you need to. All right, so let's do a few examples down here of that. So our practice problems, again, this should be really simple for the most part. G prime of x, if I bring the 4 out to the front and multiply it by the 3, we get 12, and then you reduce the power by 1, 12x cubed. That's your derivative. Okay, be careful on the next one. The derivative of h prime of x. Technically, this is to the first power. We don't usually write that, but that's what it is. If you bring the 1 out to the front and multiply it, you get a negative 1. If you reduce the power by 1, remember that the derivative of x, by the way, is 1, and that's because 1 minus 1 would give you a 0 exponent. So x to the 0 power, anything to the 0 power except for 0, is 1. So really that is negative 1 times 1, or just negative 1. So the derivative of negative x is negative 1. That should make sense because the derivative of x was positive 1, so just throwing a negative out front. Okay, m prime of x, bring the 2 out to the front, reduce the power by 1, 10x. F prime, that should actually say of x, not t, is going to be, of x, Bring the 4 out to the front. 4 times 24 is 96x cubed. Okay, now in the next few, we have to actually rewrite some stuff. So let's rewrite the function. And again, I don't know why there's a t here. That should be a function of x. Let's rewrite that as x to the 5/2 power. And then we're going to, that should be an x. Bring the 5/2 to the front. Reducing 5/2 by 1 gives you 3/2. And that's it. Okay, now the next one, we definitely have to be a little bit more careful. So we're going to rewrite this. But the whole thing is being raised, or excuse me, the whole thing, it has a cube root. So this is really going to be 4m squared all to the 1/3 power. Now we can distribute that 1/3 power to the 4 and the m squared since they're products in there. There's no additions or subtractions. So this is going to be 4 to the 1/3 m to the 2/3. 4 to the 1/3, that's just a constant. M to the 2/3, that's a variable. So when we go to take the derivative, 4 to the 1/3, or the cube root of 4, you can write it either way, is going to get multiplied by, bring the 2/3 out to the front, reduce the power by 1, so you get negative 1/3 power. That is a 1. And that's it. There's really no way to combine that 4 to the 1/3 times 2/3, since the 4 to the 1/3 technically is a cube root. So that's what that one looks like. Okay, same idea. We're going to have to rewrite the f of x down here. So that'll be 3 times x to the 7/2 power. Now I can go ahead and take the derivative. F prime of x. Bring the 7/2 out to the front and multiply it by the 3. 7/2 times 3 is 21/2. X to the, that's going to be 5/2 now when you subtract 1. And then the last one, the only thing you have to be careful about, because I see a lot of people try to do this, when I make this thing a negative exponent, the only thing I'm bringing to the top is the x to the 4th. The 3 itself is not going to be brought to the top because it's not a negative exponent. It's not anything we have to worry about. So really this is going to be 2 over 3 x to the negative 4. Don't bring the 3 up with it. It's not part of the thing being raised to the 4th power. So then I can go ahead and take f prime of x, bring the negative 4 out to the front and multiply it by 2/3, so you get negative 8/3, x to the negative 5th. Again, don't forget to subtract 1 from the exponent. Okay, I hope that all that made sense. Let's go ahead and finish this off. We're just going to do this in one video. So we have the sum and difference rules. If f and g are both differentiable, again, meaning that the derivative exists and you can take the derivative, then you can write the derivative of two functions being added together and separate and separate them. So I can do the derivative of f of x plus the derivative of g of x. It just means you can separate each individual function and do its derivative. Subtraction works the same way. It's going to be the derivative of f of x minus the derivative of g of x. So you can split addition and subtraction of functions and do each derivative independently and then put them back together again. So let's look at the practice problems. For the first one, f of x is 5x to the 4th plus 3x squared. So 5x to the 4th's derivative is going to be 20x to the 3rd. 3x squared's derivative is going to be 6x, and since I'm adding, I just add. That's it. I took the derivative of each piece independently, and I've gotten my derivative of f prime of x. Okay, same idea for h. H prime of x, the derivative of negative 2x cubed is going to be negative 6x squared. And then plus the derivative of x squared, which is 2x. The derivative of 6 is a constant. The derivative of that is 0. We don't need to write plus 0 at the end. That's it. And then the last one, g prime of x, is going to be bringing the 3 out front, multiplying it by a third is 1. So it's 1x squared. I don't need to write the 1. The next one is going to be minus 20, because that's what negative 4 times 5 is, x to the 4th, plus 4/5 x to the negative 1/5. And then in the last piece, I've got negative 3 times negative 2/3. That's going to be 6/3 or 2. So that's going to actually be plus 2 x to the negative 5/3, subtracting 1 from 2/3, negative 2/3. And then the derivative of 6/7 is a constant. It's 0. So there we go. All right. The last piece is here. This is just kind of thrown in there because it might occur on some of your homework or web assign. But the derivative of e to the x, and this will all be explained and proved later, the derivative of e to the x, my favorite all-time derivative, is e to the x. The derivative of e to the x is itself. It's actually one of the coolest functions ever. So there we go. The derivative of e to the x is itself. You just need to kind of know that one for now. We'll prove it later. Okay. Last things that we're going to do is we are now going to find the equation of a tangent line to the graph of the function at x equals 1. So remember when we found the equation of a tangent line, you needed 3 things. You needed the slope, you needed the x, and you needed the y. Well, they gave us the x. We can easily find the y. If I plug 1 in, so y evaluated when x is 1 is going to be 1 plus 1 or 2. So I now know that I have the x and the y value. I've got 1 and 2. What I need is the slope, but slope is derivative. So we're going to take the derivative. So y prime is 3x squared plus 1. Now I need the derivative evaluated when x is 1, because I actually need to have the slope at x equals 1. So y prime of 1, plugging a 1 in there is going to give you 3 times 1 squared plus 1. So that's going to be 3 plus 1 is 4. So now I have the slope, I have the x, and I have the y. So now we can write the equation. Y minus y1, which is 2, equals slope, which is 4, times x minus x1, and that's the equation of the tangent line. Okay, one more. So we know we need to find the y value. So let's go ahead and find the y. So y of 1, when x is 1, is going to be 1 minus 3 plus 2, which is actually going to be 0. Now we need the slope. Y prime is 4x cubed minus 6x, and that's it because the derivative of 2 is 0. So now I need the slope at my x value. So plugging in a 1, 1s are, by the way, are nice and easy as well as zeros. If I plug in a 1, you're just going to get 4 minus 6, which is negative 2. So again, I have the x value, the slope, and the y value. Let's plug them in. We get y minus 0 equals slope, which is negative 2, x minus 1. And since we have y minus 0, by the way, this is right, but since we have y minus 0, we're just going to simplify that to y, and then we may as well just go ahead and distribute. So we get negative 2x plus 2. And that's it. That's the equation of your tangent line. Much easier to do now that we know this power rule. All right, that's the end of the video. A little under 25 minutes. Should be a relatively easy assignment.